Welcome to my lecture on sample proportions, and this is an application of the central limit theorem. So let's discuss this categorical central limit theorem. So here I say it's categorical because the proportion P comes from data in which we have categories or a discrete outcome, and T is the number of observations with a certain characteristic or categorical outcome. And n is your number of observations, and that's your sample proportion. It represents the proportion of outcomes that you deem of interest. Okay? And what it says is that this proportion is approximately normally distributed. Here, T represents the total number of individuals in the sample with the characteristic, and hence the observations are categorical, okay, because it's a characteristic. The probability of each individual observation having the characteristic is probability P, and the mean of the sampling distribution is P, okay. So in the central limit theorem, we're going to set mu to be equal to P, and the standard deviation is the square root of P times 1 minus P divided by n. Now, this is not a hard and fast rule, but it's a strong recommendation. If you're going to use this normal distribution, you should have that n times p times 1 minus p is at least 10. Now, it doesn't mean that you can't apply it if it's less than 10, but that if you did that, it would be a less than ideal circumstance. Okay. So ideally, this criteria should be satisfied. Okay. So here's an example. Okay. It says, according to company records, the proportion of defectives is 20%. If 100 parts are shipped, what are the odds that less than 19 parts are defective? Okay, so let's calculate this probability. So first thing that I did was I checked that n times p times 1 minus p, which is 100 times 0.8 times 1 minus 0.8 is equal to 16. And I apologize. We can do it like this, and we'll get the same number. Okay. And so I just interchange p with 1 minus p here, okay? And we'll get the same number. So the standard deviation for the sample proportion, that's 0.04, okay? So I want to know the probability the total is less than 19. Now, that represents the numerator here in this. This represents the total. I have a statement about proportions, so I need to divide by n, okay, to get a proportion. So I want to know, I want to know what are the odds that the total is less than 19. So I divide by the sample size. It's going to be 19 divided by 100. That's going to be the probability that the total is less than 0.19. So now I have my sample proportion because the total divided by n is the sample proportion. And I'm calculating the probability the sample proportion is less than 19%. Well, this probability comes from a normal distribution where the mean is the 20% given and the standard deviation is 0.04. So I just have to take the z-score. Okay, so the probability of the proportion minus 0.2 divided by the standard deviation is less than 0.19 minus 0.2 divided by 0.04. Okay, and this should be negative 0.25. Okay, and if we do this calculation, let's just use this normal distribution calculator. So the z-score has a mean of 0, standard deviation of 1, and that is below minus 0.25. Excuse me, below, so we want this one, minus 0.25 below. We're going to get 10.56%. So I apologize. Or 10.5%. Okay. And those are the odds that less than 19 parts are defective is 10.5%. Okay. So that's not great for this company. Okay. Here's another example, and we've seen this with the binomial distribution, but here's another way of answering this question. So it's accused Robert Swain of raping a white woman, and he was sentenced to death. He appealed his sentence, saying that he was not given a fair trial because the jury was all white. And it says that in this county, 26% of the eligible jurors were black, but only 8 black men among the 100 were selected for jury panel, and no black man was selected for trial jury. Okay. So here's our goal: to assess their statement that the overall percentage disparity had been small and reflects no attempt to exclude any specified number of black Americans. Okay. So let's use our sample proportion to approximate this answer. So first of all, there's a fixed number of trials, n is 100. Either you're on the jury panel or you're not. Okay. So T is going to be the total number of black Americans selected out of 100 for the jury panel. And here we're going to assume that each trial is independent. This should be a safe assumption because the law indicates that the sample must be random. And if it's random, one person's outcome should not be affected much by another individual's. Okay. The probability P of selecting a black American from the population is representative of their sample proportion, the proportion of black Americans in the community, which is 26%. Okay. And this should be a safe assumption, again, if it is truly a random sample of the population. Okay. Okay. So one thing that we should notice is that n times p times 1 minus p, that's 100 times 26 times 1 minus 0.26, that's bigger than 10. It's about 19. The standard deviation of the sample proportion, that's going to be 0.26 times 1 minus 0.26 over 100. We get 0.043. Okay. And we want to calculate the probability of having 8 or less black Americans on selected. Okay, so I start with a total, then I divide by the sample size. So that gives me a sample proportion, and I want to calculate the probability of the sample proportion is less than 0.08. I feel pretty confident about using this central limit theorem with the normal distribution. Okay, so all I do is I take this 0.08, I subtract by the theoretical mean, which is 26% or 0.26, I divide by the standard deviation, which is 0.43, and I need to calculate the probability z is less than minus 4.18, and I get a probability of 10 to the minus fifth, which is basically 0. Okay. So here's another example. And this came from an actual study in sex role stereotypes and personal decisions, in which 48 male bank supervisors attending a management institute hypothetical personnel files were given and asked them whether they would promote the applicant based on the file. the personal files were identified except 24 of them. So the files were identical, except 20 of them listed a male name and 24 of them listed a female name. So it's a match pair design. Like is one applicant, one male applicant with exactly the same qualifications as a corresponding female name. And here are the results from this study. Okay, so here's the male name versus the female name, and this was the promoted versus non-promoted. So it says here the total number of observations were 24 women and 24 males. And the probability of promoted in this study will be 21 plus 14. Okay, so it shouldn't matter. Here my hypothesis is that being promoted should not matter based on gender. So just if I look at how many were promoted versus not promoted, that's 21 plus 14, ignoring gender, okay, which is 35 out of 48 or 73%. The observed probability of a promotion if an applicant is female, if I just look at only females, that's 14 out of 24, which is 58%. That's much less than the 73%. So my question is, if the probability of promotion doesn't matter according to gender, then the true rate of promotion or probability should be 73%. What are the odds of seeing in a sample of 48 then having a proportion of only 58%? That's the question I'm going to answer. Okay. Well, I'm going to use this central limit theorem. And one thing that you're going to notice is I'm going to check n times p times 1 minus p. That's 24 female applicants times 0.73 times 1 minus 0.73. That's 4.47. So using this normal approximation is questionable, but I'm going to proceed anyway. Okay. And I could have used the normal distribution, the binomial distribution instead of the normal distribution. Okay. But I'm going to proceed anyway with using the normal distribution. It says the standard deviation of the sample proportion is going to be p times 1 minus p over n. That's 0.09. Okay. I want to calculate the probability that in 48 female applicants, the probability of promotion is less than 58%. So I'm going to calculate this probability. If I proceed with the normal distribution, I subtract the mean of 73%. That's assuming that gender doesn't matter. I'm going to divide by the standard deviation. Standard deviation should be 0.09, so my apologies. And I'm going to get this z-score, and let me recalculate that since there was an error there. And this number should be minus 166. And I can tell you, without using a calculator, that has to be 0%, because that's just way too far for, excuse me, let me just double check. Excuse me, it was actually correct. It's 1.66. Okay. 1.66, so this number was calculated correctly, and the probability of obtaining a sample percentage then is 4.7%. Okay. So that is pretty unlikely that you would see a promotion rate of 58%. So what this is saying is that if the true rate of promotion was 73% for women, and seeing a sample average proportion of promotion of 58% in a sample of 24 females would happen 4.7% of the time. So it's not impossible, but it's pretty unlikely, is what this is saying. Okay, and this is saying that this would happen, with a true probability of promotion of 73%. You'd see this occurring 4.7%. With a probability of 4.7%. Okay, so that's pretty unlikely to occur, and it would say that this difference would be to random chance, not to any differences in gender. Okay. So here would be the conclusion that I would write. It says the data is a randomized experiment, and conclusions that are drawn are likely causation. The analysis shows that it's more likely that gender plays a role in affecting the probability of a promotion, as the odds of obtaining a sample of 24 females in which the sample proportion of promotion of females is 58% or less is less than 5%. Okay, so that would be my conclusion. Okay, well, thank you for joining me on sample proportions.